It's lab time, folks. So this is going to be the full analysis of the acceleration lab, so that way you can look back and see what you've done and compare it to what I've done. So what I have here are the 4 separate possible graphs that may have been discussed. And so we've got a position time graph, velocity time graph, acceleration time graph, and the ever popular velocity squared position graph. And from these, we're going to help figure out and derive all of the exciting equations and formulas they'll be using for the rest of the acceleration unit, known as kinematics formulas. So first of all, I like to start with the acceleration one. And these are the equations I got off the computer. So this was a quadratic, linear, linear, linear. So basically, I'm going to break down what all this stuff means. So if I look, my y value is actually acceleration, equals 0.003, and if I got paid $0.003 an hour, I'm not working there. So this is effectively 0. And so this x is time, but if I have 0 times time plus 1.02, well, I'm not exactly the happiest of campers. So this all goes away. And we are left with acceleration equals 1.02. Well, that's cool. So basically it's a constant. So acceleration is 1.02, and then acceleration has units of meters per second squared. So let's put that on there. And then let's mark that for future reference with a highlighter that's hopefully not so massive. Dear gosh, can I make that smaller? There we go. Cool. All right. So that's the acceleration. So basically, that's the acceleration of my object. So now the next thing I'm going to do is I'm going to go off to my velocity time graph. I'm going to do the same thing, replace my y's and my x's with what's on my y and x axis. So y is velocity. That is not the size I wanted. Why can't this work today? So let's take 2. All right, so we've got velocity equals 1.01 times x, which is time, plus 4.95. Well, we got to have units on this bad boy. And so if we look at the units, well, velocity is in meters per second, and time is in seconds. So if we look at what the units of our slope are, then the units of our slope, would be equal to meters per second over seconds, and to make all your math teachers happy, that's meters per second squared. And, oh, interesting. So that means that this 1.01 has units of meters per second squared. So I've got a slope value of 1.01 meters per second squared. Huh. That looks pretty similar to my acceleration value. In fact, it's basically dead on. So I would then infer that my acceleration is the slope of my velocity time graph. So I've got velocity equals acceleration times time, plus, and then what's this 4.95? Well, that's my y-intercept. So that's my velocity when time is 0, which is right here. So that's really my initial velocity. So this then becomes the ever infamous equation, velocity equals acceleration times time plus my initial velocity. Well, that's cool. All right. And so again, that acceleration is exactly matched over there. So that's that. The next one I like to go to is my position time graph. And if I replace my y's and x's with what it really is, we've got position equals 0.49, and then x is time squared plus 4.92 times time plus 4. Now to figure this one out, I'm going to go about a different technique. I'm actually going to look at the units of this, and so I'm going to ask, well, what do the units have to be? Units. So if I do that, in order to add all these together, we have to have the exact same units for everything. And since the units for position are meters, all of these situations have to add up and have units of meters for this to work. So if I look, I basically have an A value, a B value, and a C value for my quadratic equation. And so we know all the units have to equal meters. So if I look at just my first value here, I really have meters, because that's my units over here, equals my A value, which I have no idea what the units of this number are, times time squared. And well, time is units of seconds. If you square that, you get that. So if I solve for A, I really get meters per second squared are my units for A. Huh. Well, that's interesting, because meters per second squared we know are the units of acceleration. So that means that my A value is probably related to acceleration, but let's see, 1 and then 0.49. This is like, that's about equal to 0.5, and that's equal to 1, so this is actually equal to 1/2 my acceleration. Interesting. All right. So now let's look at this B value here. What's the B value? Well, if I look at it for the B value, meters equals the B value times the units of time, which are seconds. So that's that. So meters per second is my B value. So meters per second, that's units of velocity, speed, probably velocity, because our position is changing over time, and we know that's velocity. So if I think it's velocity, I'm going to look at this velocity time graph over here, and the actual value is 4.92, which is kind of like 5-ish. And if I look over here, 4.95, that's like the exact same number. And I just said that that was my initial velocity. So this is actually my initial velocity. Cool. And then the C value, this is my personal favorite, takes a lot of effort. M equals C. Wait. Yeah, meters. Okay, so this guy has units of meters, so it's got to be some sort of distance, displacement, or position. And since we got a position time graph, and it's actually right here, it's basically my intercept, so I'm going to go with that's my initial position. All right, so that's my initial position. So what this really gives me here is a new equation of, I'll go to a new color, because we're kind of getting jammed up in colors here. New color, so position equals my 1/2 times acceleration times time squared, plus my initial velocity times time, plus my initial position. Alright, so that is my second equation. This was my first. Alright, so I basically have two equations. Now this one sometimes can be written as then displacement equals 1/2 acceleration times time squared plus initial velocity times time. So that's another one you'll very commonly see it written as. Oh man, it's getting hard. So again, we're building everything off of this initial understanding of acceleration. And so now I'm going over to my last graph over here. And that graph has to do with my velocity squared versus position. So let's get a new color out. Let's go red. So this here is velocity squared equals 2.03 x is, well, position here, plus 24.6. Now again, let's look at those units. So the units for slope would be velocity squared, which is meters squared per second squared, divided by the units for position, which is meters. Meters squared per second squared. And if I do this, whoops, what happened? Oh, I gotta minimize that. We simplify this guy here, and this simplifies to be, that cancels out with that guy, meters per second squared. So this slope must also be related to acceleration. So let's look at the numbers. We got a number of 2 versus a number of 1. How does 2 relate to 1? Survey says, yes, twice. That's exactly right. So this here represents twice my acceleration. So now I got to figure out what the heck does this number mean. Well, this is my intercept. So this is my initial, it's my velocity when position is 0. So it's basically my initial velocity squared. Well, we can check that because 24 is like 25, close enough. And we've said my initial velocity is 4.95, which is like 5. Well, 5 squared is 25, so that makes sense. That confirms that. So that's my initial velocity squared. So what this basically gives me is the new equation of velocity squared is equal to 2 times acceleration. And since this is a change, you gotta have a change in position here. It's really like a displacement plus your initial velocity squared. And so these are all the equations that come directly from the graphs. So now if you notice, we've got 3 out of our 4 kinematics equations determined, and they were all based on understanding what our acceleration was and making relationships between the units and the same units of acceleration, and then looking at how the numerical values compared to the numerical values for acceleration. We also made some comparisons to the velocity time graph as a whole. That leaves one last equation to derive, so I got to make some space here to make a new drawing to derive that one, and then we will call it a day. So the last equation is based off of the velocity time graph and our understanding of displacement, because displacement is the area of the velocity time graph. So if this is my velocity time graph, if I want to calculate the area of this, I'm looking at a rectangle and a triangle. So I've got object 1, area 1, and then I've got area 2, and these two combined will tell me my displacement. So the total displacement is equal to the area of the triangle, which is 1, plus the area of the rectangle, which is 2. So let's do the triangle. 1/2, the base is time. The height is my change in velocity, so it's going to be v minus v sub naught. And then plus the area of a rectangle, which is a little easier because my base is time and my height is my initial velocity. So now I'm going to just do some algebra. Okay, so let's pause for a station algebra break. Whoa! Okay, I got scared there. Whenever algebra shows up, it scares me. So here, I'm just basically walking through. I made my equation here, and I'm just doing a lot of algebraic substitution, manipulation, and rearranging of variables, and I eventually get this final equation here. And so what that leaves us with are the 4 kinematics equations. So I'm going to rewrite these so we have access to them. So one of our kinematics equation is displacement equals initial velocity times change in time plus 1/2 acceleration change in time squared. Another one for displacement is 1/2 your initial, final, I reverse those, times time. And then we've got 2 that start off with velocity. So velocity equals your initial velocity plus acceleration times time. And then we've got velocity squared equals our initial velocity squared plus 2a times my displacement. So these are all the 4 kinematics equations that we'll be using in class, and this is where they come from. Very exciting stuff. If you were to write a lab write-up on this, hopefully it looks something like this. So have fun and do more physics.